So Jose Perea is an associate professor in the Department of Mathematics and the Curie College of Computer Sciences at Northeastern University. Prior to Northeastern, he held positions as an assistant professor of computational mathematics, science and engineering, and mathematics at Michigan State University, and as a visiting assistant professor of mathematics at Duke University. He holds a PhD in mathematics from Stanford and a Bachelor of Science in Mathematics from Universidad de Valle, Colombia. He is the inaugural 2022-2024 lecturer for the Mathematical Association of America and the National Association of Mathematics, a recipient of the 2020 NSF Career Award, and a 2020 honoree of Latisms, and furthermore, a 2018 honoree of Mathematically Gifted and Black. On a personal note, I've had the great pleasure of knowing Jose since I think about 2006, 2007, when I was a potentially annoying undergraduate student, and Jose was a young graduate student, and his cohort of graduate students sort of took me under their wing, for which I'm grateful. So Jose, please take it away. He'll be telling us about a topological study of the space of planar pentagons.
Thanks, Henry, and thank you to the organizers for the invitation. I think computational chemistry produces some of the most interesting sort of data science problems when you look at them from the lens of geometry and topology. So what I hope to do is run through an example where I think topology can help in sort of that type of problems coming from computational chemistry. So the genesis to this talk is the following example. So think of the cyclooctane, which is a molecule with a sort of ring of 8 carbons, and then you have sort of 2 hydrogens attached to each carbon. And you can think of all the possible realizations of this molecule in R3, sort of all the valid realizations. So if you regard 2 conformations as being the same, if you can go from one to the other with a symmetry of Euclidean space of R3, then you get the conformation space, right? The collection of all possible conformations up to symmetry. And a natural data science question is, what is the shape of that conformation space? Okay, what is the shape or structure of that conformation space? So in a paper from 12 years ago, Sean Martin and collaborators showed that the conformation space for cyclooctane is in fact a sphere, a 2-dimensional sphere with a Klein bottle attached to it, right? So it's a very complicated space from a sort of geometry and topology point of view. Here on the left, I'm showing an isomap representation of a data set sampling the conformation space. So again, each dot in the figure on the right is supposed to represent one of these valid conformations up to symmetry. And what you would like to do is sort of do the same thing for other and bigger molecules. Okay, so that's the genesis for the talk. And again, the question is, how can topology help in these types of problems? The example I want to use, which is something that mathematicians do all the time. If you cannot solve a hard problem, go to a simpler problem and see what you can say. So the simpler problem I'm going to walk through today is the space of planar unilateral pentagons. Similarly to the cyclooctane example, our data set is going to be a collection of pentagons on the plane. The side lengths are 1. And we deem 2 such pentagons to be the same if you can sort of put one on top of the other up to some rotation and translation. Okay. The colors are a notion of, at least morally speaking, a notion of energy. The darker it is, the lower the energy, you would think, and the lighter it is, then the higher the energy, you would think. So I'm going to switch between slides and code, and hopefully it'll work out. So bear with me while I switch to another window. So hopefully now we're seeing some code Okay, great. I'm going to go ahead and again just remind you what the data set is. It's the collection of pentagons on the plane with side length 1, and then 2 pentagons are deemed to be equivalent if you can rotate/translate one onto the other. Okay, so I'm just going to go ahead and load up the data, and here are some of the examples from the data set, again colored by energy. There are something like 14,000 such pentagons, and if you wanted to analyze this data set, the first thing you would do, or at least the first thing I would do, is to run principal component analysis, right? PCA, just to get a sense of what the data set looks like. So if you look at the explained variance, then you will see that the first few principal components explain quite a lot of the variance of the data. And again, when you plot it in R3, this is the picture that emerges. Okay. So again, each dot in this plot is supposed to be one of these pentagons, and the color is supposed to be representing the energy of the pentagon. Okay, so how regular it is. So if folks have ideas on the chat as to what the space ought to be, please put them there, and we can use them for the discussion. It's a beautiful picture, though. The first sort of observation is that you have self-intersections, right? So you have places where the energy goes from one color and then jumps to the other. So this is not a very successful dimensionality reduction, right? Because it is sort of crushing information that shouldn't be crushed. Okay. But nonetheless, it seems that the space perhaps is something like a surface or maybe something more complicated. If PCA doesn't work, try something more difficult, right? So here's isomap, another dimensionality reduction method that people used. And notice that I'm actually taking a subsample of the data. So I'm not using the full 14,000 because isomap is slow, but I'm using something like 4,000, about a third of the data. It doesn't look as pretty, but we get some pictures, right? It looks like a coffee mug. Still, not a lot of information. So PCA fails, isomap fails, and then the last thing I'll try before moving on is LLE, sort of another yet more complicated dimensionality reduction method. And this is the picture that emerges. Right, so still a pretty picture that you can do some art with, but not a lot of mathematical insight. Okay, so it's still crushing the data. So I'm going to switch back to the slides, and what I hope you have sort of gained is sort of perhaps the idea that the space of planar pentagons is difficult, and we want to analyze its geometry and its global topology. Okay. So how do we do that in algebraic topology? So I thought this was the first talk of the topology series. So I would start very basic. So two of the most basic shapes we see in topology are on the left, the sphere, and on the right, the torus, which is the surface of a donut. One quantity we can compute about shapes are the so-called the Betti numbers, which measure the number of holes that you have in your space, okay, in each dimension n. So for example, Betti 0 measures the number of connected components or the number of clusters you have in your space. Both the sphere and the torus are all connected, so they both have Betti 0 equal to 1, right? Just one connected component. Betti 1, on the other hand, measures the number of one-dimensional holes. So how do you measure that? What you do is you go ahead and draw closed curves over your space, and you ask whether or not that closed curve bounds a filled-in region. On the sphere, any closed curve bounds a filled-in region. So Betti 1 of the sphere is 0. There are no holes. However, on the torus, you have sort of two closed curves, the blue and the red, such that you can pass your hand through those curves. So we think of them as holes. And that's why Betti 1 of the torus is equal to 2. And then finally, Betti 2 is asking about two-dimensional holes. And the sphere itself is sort of a closed surface bounding a three-dimensional void, and the same for the torus. It is a closed surface that bounds a three-dimensional void because the torus is hollow. And again, the main point is that you can use the Betti numbers, which again are named after Enrico Betti, to distinguish between spaces, right? So if two spaces have different shapes, different topologies, then actually the other way around. If two spaces have different Betti numbers, then they will have different shapes, okay? And then what we hope to do is compute similar things for data. You hope to compute things that look like the Betti numbers for point clouds, like the ones coming from the cyclo-octane space or the space of pentagons. Okay. So it actually took the genius of sort of one of the the top mathematicians in history, Emmy Noether, to realize that the Betti numbers are actually the shadow of a more complicated object, which are called the cohomology groups of a space. And the reason why I bring these guys up is because they will be useful towards the end of the talk. Okay, so what the cohomology of a space is, at least for now, is a vector space. You get a vector space for each n, and the dimension of that vector space, in fact, recovers the Betti numbers. So again, the nth cohomology is going to give you a feature for shape in your space. So with that information in hand, we can go back to the torus and the sphere and replace the Betti numbers for the actual vector spaces that should have been there to begin. Okay, so you have the dimensions, and now you actually have the vector spaces, which is the same thing. Okay, so let's see what it would take to do this exact same thing for data. Okay, so imagine that you have a data set like the one you're seeing on the screen now. And again, imagine that each data point is perhaps one of these molecules we're interested in. If you were to compute the Betti numbers directly, you would get not a lot of useful information, right? Betti 0 is supposed to measure connected components. So it should be the same as just the number of data points because everything is disconnected. And Betti 1, which is supposed to measure cycles or one-dimensional loops, should be equal to 0 because the space again is completely disconnected. So you do the sort of obvious thing, which is to try to build connected spaces from your data, right? So what you do is, if two data points are very close, you draw an edge between them. If three data points are very close, you draw a triangle between them. And then you allow yourself to change the notion of how close you take things to be able to join. And what I want you to notice is that at some point, the circularity of the data is now apparent. And now the Betti numbers will give you sort of interesting information. So again, the name of the game is going to be, let's take our data set, join things that are close with edges, triangles, tetrahedra, and so on, and see the evolution of topological features such as the Betti numbers and the cohomology. Okay, and this is perhaps one of the deepest idea in the talk. So again, look at your data set at all scales by building geometric complexes on top of them using closeness. So one thing we can do right away is compute something like the Betti numbers, which again count the number of holes in your space. Okay, so if you keep track of that count of number of holes, what you can actually do is you can track how they change across scales using the cohomology as the best invariant, right? So instead of thinking about the Betti numbers as dimensions, I actually think about the cohomology vector spaces and how the vector spaces change across scales. And what the algorithms do is essentially they track how the basis elements are related to each other from one scale to the next. So the picture that you're going to see repeatedly as we get towards the end of the talk is the following. we are tracking how basis elements change from one scale to the next. And in particular, we look at them across all scales at the same time. So if you see sort of a bar that is very long, that indicates that you have sort of a topological feature that is sort of stable or consistent across scales. And therefore, it is an indication of something truly going on with the data underlying the construction. Does that make sense? So the barcodes are the things that we're going to compute, and we have algorithms for doing so. So going back to the Taurus and the cohomology of the Taurus. Yeah, so I had told you that if you took a Taurus and you computed its cohomology in dimension 0, you had sort of a vector space of dimension 1 because you have one component. In dimension 1, you had a vector space of dimension 2 because you have these two holes in the Taurus. And in dimension 2, you had one hole because, again, the Taurus was the surface bounding one empty space. So if you do the experiment of sampling data from the Taurus and computing the barcodes, you get the picture on the lower right. So again, I want you to concentrate on sort of the horizontal bars, which are supposed to encode topological features across scales. And what I want you to notice is that in each dimension, sort of barcode in dimension 0 has one long bar, barcode in dimension 1 has two long bars, barcode in dimension 2 has one long bar, that this count is consistent with the cohomology and the Betty numbers. So the barcodes are exactly how we applied topologists try to infer the topology of the underlying data set. We compute barcodes and try to guess what the underlying space is. Okay, so that's the game we're going to play. And I guess people call these the persistent cohomology of data. So let's see. Okay, so I'm going to give you a basic example, and then we'll go back to chemistry examples, which are harder. So think of the following data set, just a collection of little duckies, or just one little duck, and you take photos of it in different positions. Okay, so that's the data set. Each image is a 128 by 128 matrix. If you compute the barcode, this is what you get. You get a long bar in dimension 0 and one long bar in dimension 1, right? So that is telling you that the data is likely connected, and it has sort of one prominent hole in dimension 1. If you were to do PCA on this data set, you would get the picture on the right. So this is telling us, right, the computation of the barcode is telling us that we should have something circular, something with one-dimensional hole in it. And the PCA visualization is agreeing with that computation. So what we're hoping to do is we're trying to utilize topological signatures, like the barcodes, to guide and tell us if the dimensionality reduction procedures we're doing make sense. Okay? So another way to present these barcodes is the so-called persistence diagrams. And it's just another way to sort of display the same information. So instead of a bar starting at A and ending at B, you plot a point with coordinates A, B. And now the length of the bar is the same thing as the distance from the point to the diagonal, right? So long bars are replaced by points far away from the diagonal. So that's how barcodes are going to be represented. I was tempted to tell you about another example, but I'm going to resist the temptation so that we have enough time to discuss the mathematics. So going back to the example of planar pentagons, here is what the persistence looks like. Okay, so you have 8 dots in dimension 1. You have 1 dot in dimension 0, right? So it's telling you you have 8 one-dimensional holes and one two-dimensional hole, right? So it's again, we knew it was a complicated space, and the barcode or the persistence diagram is not telling us, what the space is right away, unfortunately. So we need sort of other tricks to get to the final answer, and we're actually very close to it. So here's what the tool we're going to use is called. So this is part of a paper from a couple of years ago, and what the paper does is it leverages the following theorem. There's a beautiful theorem in algebraic topology. One of its consequences is the following. If you compute the cohomology of a space, that's the thing on the left, that is the same thing as homotopic classes of maps to the circle, okay? So if you don't know what those words mean, don't worry. The main takeaway is that you can compute one of these cohomology classes, right? So one of these topological invariants and get maps to the circle representing sort of the algebraic class. And what we've done, sort of the contribution is to realize this type of theorem in algorithms. So what does it mean? So it means that you're computing, instead of cohomology, you're computing persistence cohomology. So you're computing these barcodes or these persistence diagrams. And the idea is that if you take a class that is sort of very persistent, that has a lot of information about your data, you can use it to build maps from your data to the circle. So that's the game we're going to play. Replace persistent cohomology computations, grab the class that you see as very persistent, and use it to build maps from your data to the circle, again, in such a way that it represents the class. So here is the data set of little duckies again, and they are ordered in some random order, right? There's no structure to the sequence of duckies. So if you were to play a video with the duckies, ordered in whatever way you got them, then you get a nonsense video, which is very sad. But we computed, persistent cohomology, right? And we saw that we had one class that was very persistent. And that class was, representing the fact that the data lies around a circle. So you can take that class and use the circular coordinates algorithm that I haven't described because that's not what we're here for. But the consequence or the result is that class will give you a map from the data, meaning the collection of images of little duckies, to the circle. Okay, so that's the main thing. And now we're going to order the little duckies according to their circular coordinate. And this is the video that emerges when you do that, right? The little duckies are being played in the order of the cohomology class we found. Okay, so if you're thinking, how does this relate to computational chemistry? I thought that's what we were here for. So what this is doing is finding the intrinsic coordinate for the system, right? So you start with all these images. We computed a topological invariant of it, persistent cohomology, and used it to derive the intrinsic parametrization of the data set. Okay. So let me, for the finale, let me go back to the code. Okay. So how much time do I have, Henry?
1 minute.
1 minute. Oh, Jesus Christ. Okay, so we're gonna go back to the cyclooctane, not to the cyclooctane, to the space of pentagons. Okay. So now you know enough to follow the code. I computed the persistence diagrams. And as I said, you get 8 classes in dimension 1 and 1 class in dimension 2. How do I know that you have 8 little dots in here? Because you can just compute, how many things you have that are large. So 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 dots that are very far from the diagonal, and the other ones are very close. And the same in dimension 2. Okay. So what we're going to do is, again, use these classes that we have computed to build circular coordinates from the space of pentagons to the circle. So that is happening, and it already happened. So this is the picture that emerges, right? So I want you to go back to the initial, say, PCA dimensionality reduction, which was beautiful but complicated. The perhaps isomat picture that is not as beautiful and maybe as complicated, and the LLE picture, sort of not very useful. But here's the sort of the consequence for the space of pentagons. So what are the coordinates? Each axis is a circular coordinate. So think of the x coordinates, the x coordinate as going from 0 to 2 pi, the y coordinate going from 0 to 2 pi, and the z coordinate going from 0 to 2 pi. And 0 and 2 pi are the same in all places. Okay, so the left sort of wall is the same as the right wall, the bottom wall is the same as the top wall, and the back wall is the same as the front wall. So what you will see, first of all, is that there are no self-intersections. So we are realizing the data as it should be in the three-dimensional torus. Step 2, if you follow the identifications, the bottom identified with the top, the right identified with the left, and the front identified with the back, what you realize is that the data is actually a surface of genus 4. So it's a torus with 4 holes in it. Okay, so it's a very beautiful surface that we got to using topology. Now, if you write just some lines of code, you will be able to actually place the original images in the points where they are. So you can make sense in this new coordinate system of how the pentagons really make up a surface of genus 4. Going back to the computational chemistry, this is a metaphor for looking at spaces of conformations of molecules and trying to figure out what are the intrinsic coordinates so you can do dynamics with fewer coordinates. Okay, so let me end there, and thank you all for your attention.
Thanks very much, Jose. So let's give him a virtual round of applause. And I think we have time for maybe 1 or 2 questions before I pass it back over to Amir for the discussion period. So questions for Jose?
I've got one. It's been a really interesting chat during your talk, Jose, and I've really enjoyed it. And I think that, you know, this touches on so many different aspects of what computational chemists think of in the context of dimensionality reduction for potential energy landscapes. And you know, sometimes we do that dimensionality reduction for lots of different reasons, right? Sometimes we want to try and find the best intrinsic reaction coordinate, but sometimes that intrinsic reaction coordinate is a higher dimensional object, right? And not as reduced as the chemist might go to in the context of just distances or angles. Another thing that I was thinking of as Henry and I were chatting, and as you were talking, is, you know, another way to maybe frame this or think about this is, you know, you could ask the question, if there is a way to, and I'm going to try and frame this correctly, is there a way to maybe do a mapping or a dimensionality reduction that is most likely to lead to a certain type or a certain cohomology of that space? So if you wanted to, like in the case of this sphere with the Klein bottle attached, is there a way to maybe think about what input representation is most likely to lead you to a reduced representation that looks most similar, for example, to a Klein bottle or a sphere with a Klein bottle attached. Because, you know, you can depending upon the DR, you could get to lots of different shapes, right, of the conformational space.
Yeah.
And so some of them are going to lead to certain shapes versus others. And I'm just wondering if there are ways to think about how you might try to find a DR that would give you a certain shape of the conformational space. Does that make sense?
Yeah, it does. It does. So I think another way to frame what you described is what is the thing you want to preserve when you are doing DR? By DR, we mean dimensionality
Exactly.
reduction.
Yes, exactly.
Dimensionality
Exactly.
reduction, right? So you may want to preserve linear structure. And that's what isomap, that's what PCA is doing. It's doing a linear projection. So it is preserving linear structure. If you're doing isomap, it is preserving distances, you know, particularly local distances. What the circular coordinates algorithm I described preserves is topology. It preserves the cohomology classes that you started with, and in particular, the ones in dimension 1. So what I'm advocating for is, let's compute topological invariance of these data sets, and then design dimensionality reduction algorithms that preserve some of the things we have found as descriptive of the data. So I gave you some examples. Circular coordinates preserve circles, but we have things that preserve other things like toroidality, sphericalness, and other.
Very nice. Okay.
And I didn't get to it, but perhaps I should just show you one slide. It is let's see if we can get one slide up. Is this slide? So hopefully you're seeing my slides.
Oh yeah.
Okay, so yeah, I actually should have shown this. So the library that has the code for what I showed today is called DryMac, which is it comes from dimensionality reduction with Eilenberg-MacLane spaces. And what it does is it takes cohomology classes like the ones we found with persistence and produces coordinates to interesting spaces in a way that preserves the topology.
Oh, that is very cool.
Right?
Thank
So
you.
this is it. Yeah, thank you for the question.
Very nice.
Thanks, Aurora, for the next question. So there's a question from Sapna in the chat, and I see Andreas has his hand raised, but let me pass it back over to Amir for the discussion, and maybe these questions from Sapna and Andreas might come in the discussion. So Amir.
Yeah, it's you and Sapna. I mean, thanks for both wonderful talks. I mean, you just can continue running the show, so.
Sapna, then please go ahead.
Okay. All right. So I'll ask my question. Jose. I was curious as to how I should think about these intrinsic coordinates, and then how would one consider using them for dynamics. And I think really what I'm thinking about is, are there ways of interpreting and understanding what these intrinsic coordinates are?
Right. So yeah, that's an excellent question. So what we got to was this idea that, at least in the example of pentagons, and think of it as the template. So we found a low dimensional parametrization of it. And again, the colors are supposed to be energy. So if you wanted to think about dynamics, you're thinking about the lines of some gradient, of some vector field. And then what you want to leverage is that if you're in a lower dimensional space, like in this case, the 3-dimensional torus, then the estimation of these flow lines is numerically more stable. And there are other tricks that you can play, again, because the low dimensionality allows you sort of computational geometry tricks that you don't have access to in high dimensions. So that's one way. Another thing is that you really want to interpret the final coordinates you're getting through this dimensionality reduction. And I guess that's why I showed sort of the last bit of code where you could actually hover over the dots and get a sense of what the parametrization is doing. I don't know that we have a good automatic way of giving the semantic meaning of the coordinates, but I think you actually need to go in there as a data scientist and stare at it and try to figure out what the coordinates are doing. Yeah, because there's so much going on in the middle that, and this happens all the time in data science, that it is hard to interpret the thing that you're computing at the end. But if it is low dimensional enough, perhaps the human can do something.